Today, we want to talk about area and volume. I know I spent a lot of time already talking about area, but I want to talk about volume. We want to start riffing on this theme. Remember that integration is multiplication, but one of the factors is continuously variable. So any applications of multiplication are applications of, I spelled integration wrong. I must have been thinking of algebra. There. I'll edit that out later. Actually, I won't. I don't edit video. I've already hit record. It's going in. Applications of multiplication are applications of integration because integration is just multiplication, but one of the factors is continuously variable. Two problems with that. It's variable and it's continuously variable. If the only problem is variable, it has different values, then we just get to use addition. We don't get to use multiplication. We have to step one back to addition. That's probably what I was thinking when I wrote addition. The continuously variable part is where we have to start integrating things. So we've talked about area quite a bit. Area is equal to length times width. This is the only application of integration that we really need. This is the only formula for area that we really need. Because now that we have integration, if area is equal to length times width, just the base definition of what area is, if length is continuously variable, we integrate the length over the width. So we're going to do the same thing with volume. Volume is cross-sectional area multiplied by height. The game that we're going to play here is the same as we played before. So just like before, one of these factors will be continuously variable. The game that we're going to play is to make one of these factors continuously variable. In the case of area, it didn't really matter which one we called the continuously variable one. Since we are in single variable calculus, when we want to calculate volume, it's our cross-sectional area that has to be variable. So because we are limiting ourselves to single variable calculus, this is the one that we will make variable. So we are going to be making the cross-sectional area continuously variable. We have to do this one instead of the height. We're going to write the area as a function of the height. But we have to do the cross-sectional area because we only get one variable. Moreover, because we've decided to make things hard on ourselves and just allow a single variable, the cross-sectional area is going to have to maintain its shape. It can alter its size, but it has to maintain its shape. Because once again, we're doing single variable calculus. We're going to make things easier on ourselves by making things harder on ourselves. So what I mean is that the area will always be a circle, or the area will always be a square. So the area will always be a circle, or the area will always be a rectangle. Our cross-sectional area will always have the same shape, but it's going to vary in size. Just want to lay our ground rules for how we're going to deal with this volume problem. Our strategy is going to be to write the area as a function of the height. Just like in the area problem, we wrote the length as a function of the width. We're going to write the area as a function of the height. Because the cross-sectional area will be variable, we don't get to multiply the area times the height. We have to integrate the area over the height by writing the cross-sectional area as a function of the height. Note that this is something that we are already familiar with. It's not new that volume is the cross-sectional area multiplied by the height. Most of the volumes of things that we know all come from this. So recall, the volume of a rectangular solid is the length times the width times the height. Length times the width is the area of one of the faces. We just multiply the area of one of the faces by the height. The volume of a circular cylinder is pi r squared times h. Pi r squared is the area of a cross section. So here are two volumes that we already know about that fit this description. Volume is cross-section area multiplied by the height. We're just taking an area and projecting it through another dimension. It's taking this area of length times width and multiplying by the height. In the case of a cylinder, We just take the area of this cross section, pi r squared, and multiply by the height. This is just how we do things. In the case of a rectangular solid, any two can be the area of a face. I could do length times height as the floor, and I could project that through the width. I can do the width times the height as one of the sides and project that through the length. So any two of our length, width, and height will make an area. Any questions? How's everybody okay? Too much for a Monday? It's length times width times height. It cannot be like too much for a Monday. I took you back to geometry. So we just have to be cool with this. All right. So the idea is that we're going to take a, we're going to build a shape by having the cross-sectional area always be the same shape. We're going to build a solid by having the cross-sectional area always be the same shape, but give it different sizes. So for example, oh, I forgot. We already know the volume of a cone, but we're going to calculate it anyway with our technique. Because the whole point of doing the math class is not to find out the volume of the cone. We already know that. How can we use the technique that we're trying to learn to verify something that we already know? How can we prove that our technique works? How can we verify that our technique works? We try it on something that we already know. So we already know that the volume of a cone is 1/3 pi r squared h, because that 1/3, we're doing the same thing building a cone that we did making a triangle out of a rectangle. We're picking a point on one side and extending it out to the whole other side. So when we have a cone, we have a circle, and then we pick a point on a circle. We could think of this circle as a piece of a cylinder. We just pick a point on the other side of the cylinder and connect the whole circle down to that point. So we can imagine a whole cylinder out of this one. But there are two things that we need. To measure a cone. We need its radius, the radius of its base, and its height. The thing that we want to notice is that if we take a cross section, in this case, let's say I cut it horizontally, a horizontal slice of this cone is always a circle. If we take a horizontal slice of this cone, the shape is always a circle. The radius is variable, but the shape is always a circle. So we can always say that the area is pi r squared, but the radius is variable. So the area of a slice is going to be pi r squared, but r is variable. It's not the fixed radius of the cone. It starts off at capital R at the top, and then it shrinks down to 0. So up here at the top, the radius is capital R. Down here at the bottom, the radius is equal to 0. So I switched part way. Capital R will be the fixed radius of the cone, the radius of the base. Every horizontal slice is going to be a circle with an area of pi r squared, and then r varies from capital R at the top down to 0 at the bottom. This is what I meant when we are going to be our slices, our cross-sectional area will be variable size, but the same shape. Our cross-sectional area will be variable size, but constant shape. How's everybody okay? It's hard to tell, it's Monday, so everybody kind of has that Monday stare. Everybody has that looks like, oh, whatever happened to nap time? I remember going to school like in kindergarten, and I got a certain point. You said, all right, let's turn the lights off and we'll all take a nap. Whatever happened to that? I want that back. I know Genentech, you can have nap time. At Genentech, there are certain places, they have like little sleeping pods. And if you need to go take a nap, you just go in these little pods. And I think you can turn on like white noise, and it's supposed to be like a quiet room, so you're not supposed to be in there like talking and shit. You just go in there and you can take a nap. Which for some reason, that's okay. But it is kind of dangerously close to being like, oh, why don't you just sleep here? Just devote your entire life to the company. Boy. I haven't spent a lot of time in the library here at Skyline, but I am sure that some of you know the best places in the library to take a nap. It's been a long time since I was on the Cal State Hayward campus. It's been a long time since I was at the Cal State Hayward campus, but I always knew I had a list of places that I could go where I specifically go there and not be disturbed and take a nap for an hour. Wherever you end up going to school, you've got to find those places. I'm going to switch to capitals representing the fixed radius and height of the cone. Don't worry about the structural soundness of my height holding this thing up. It'll be fine. It'll be fine. I know it's a little bent out. As long as it's not too windy outside, it'll be fine. Oh, wait. Shit. We'll be fine. We'll be fine. So, if our radius was constant all the way down, we would just have a cylinder and we would get to multiply pi r squared times h, and we would be done. Problem is the fourth grade problem. It's just multiplication. We know how to multiply. The problem here is that at different heights, the radius is all different. The radius starts off at capital R and drops down to 0 by the time we get to the other end of the cone. The only thing we have going for us right now is that the shape is always a circle. So the area of this slice I never give myself enough space to draw my radius in. It happens every year. And unlike Tony Stark, I don't learn from my mistakes, apparently. That's a worse circle than I had before. Dang it. At least my H seems more structurally sound. There we go. I know it seems ridiculous to be drawing this, especially when I'm using the computer to present this. I go, why don't you just get a video of a cone and have it animated? Because the point is not me drawing the cone badly. The point is y'all drawing the cone badly. When you draw the cone, you see how the cone is built. If you just watch, then you don't really have a hands-on in building the cone. You just have you're thinking about the cone, but you're not thinking about the cone with your hand. It's the difference between writing and typing. You engage a different part of your brain when you're typing than you do when you're writing. That's what's useful about taking notes. It's not to review for later. It's to engage your brain now. You know what I mean? Draw it lower. It's even worse because I know I'm going to be abandoning this for a 2D view in a moment. Yeah, well, shit. Nothing to do. But I want you to see this 3/4 view because the area of that slice, that's going to be pi r squared with a little r. So the area of the slice is pi r squared. Now, the radius continuously changes from capital R at the top down to 0 at the bottom. And we can see from the side, it's going to be a nice linear change. So at least it's going to be simple. For those of you playing at home, if you think I'm going to take these nice linear sides and then change them to something else, you are absolutely correct. We're still going to have a circle, but instead of the H and R being linearly related, we're going to switch them to something else, like maybe a circle or a parabola. We're just going to change the relationship with the function of the side to the radius, or the height to the radius. But we got to get our thinking in play. Fortunately for our heroes, the thinking about this is the same thinking that we always use with integration. We deal with the continuously variable parts by making things constant. Constant takes out the variable part, constant takes out the continuous part. We're going to take this area and use it as, and think it's constant for some small change in height. So I want to use area times height. So I'm going to assume that the area is constant for some small change in height. I'm drawing a gigantic change in height here because we want to see the cylinder that results. I'm going to say that small change in height is delta H. So then I can say that the volume of this slice is going to be the area of the slice times the height of the slice. And at this point, we've dropped our cone from this nice continuous, these nice smooth continuous sides to a low res version of the cone. We're just going to imagine the cone as a low res version of the cone. So the low res cone is just a stack of cylinders. The thinking here, we're imagining this cone as a stack of cylinders. A low resolution cone is a stack of cylinders. It comes from pi r squared times h. There's the cylinder showing up in a formula form. We built this in this thought experiment by taking that pi r squared, that slice, that circular slice, and maintaining a constant area through some change in height. Any questions? What we need to do now is write the radius as a function of this variable h that we created. We need to write the radius as a function of the height. That means I need r as a function of h. That means I need a variable h. we need to define the variable h. Remember, capital H is just the fixed height of the cone. Capital H is just like 10 feet. I don't want the cone to be that big. Very big. 10 inches. Capital H is a fixed value. Little h, the variable little h is going to be different heights along that cone. There are a few places that we actually know. There are an uncountable infinity of places we could define h. There are only two that kind of make sense in the context of the problem. So we are going to define the variable h. Right now, h is just some vertical variable that we're defining. Let's make h the distance from the tip of the cone up to the slice. This is one choice that we can make. We are choosing to make h the distance from the tip to the slice. This raises the question, what if we make some different choice? We have to do that problem as well. Here are the things that go along with making this choice. Once you decide where your variable goes, you have made two important decisions. You've decided where 0 is, and you've decided what direction is positive. So by making this choice, h equals 0 down here at the bottom. And by making this choice, we have decided up is the positive direction. Then the last value of h that we come across is up here, where h is equal to capital H. Making this choice, when you decide where your variable goes, you've decided where 0 goes, and you decided what positive direction is. So one end is 0. Other end is slice. And slice is in the positive direction. These are the things that you chose to make happen when you chose to put the variable where you did. I realize in the initial problems, the book tells you where to put the variable because they don't want you to have this important exercise. They don't want you to think that you have choices. I just want to explain what the consequences of your choices are. When you decide where to put the variable, you're deciding one end is 0, the other end is the slice. So you're deciding where 0 goes, and you're deciding what's the positive direction. I just realized that H was all green. Delta H was green. So it should be green. It's okay. The green and the orange are really nice together. It's like some different 3D. So we have to define where our h is so we can write our radius as a function of h. Now, we know that since we got these nice straight sides, because we're making a cone, we're going to make a linear relationship. When h is equal to capital H, that's when a little r is equal to our little r is equal to capital R. Down here at the bottom where h is equal to 0, that's where little r is equal to 0. So if we want to write r as a function of the heights, we can just use proportional triangles. We can say little r over h is capital R over capital H. This is us writing the radius as a function of a height. I need some relationship between little r and little h. And we're using similar triangles. So this allows us to write little r as capital R over capital H times little h. Now I have the radius as a function of the height. When the height h is equal to 0, our radius is equal to r over h times 0 or 0. When little h is equal to capital H, the capital H's cancel out, and we get little r is equal to r. And we'll make nice linear signs because we're looking at similar triangles. Now we can go back and write our volume of the slice. So we have pi times the radius squared and the radius r is r over h times h. I'm not sure this is the color scheme that I want to use moving forward, but it'll do for now. I think we're going to be doing this, the slice, in the base color. So in red, we have the pi r squared for the cross-sectional area. The height is the delta H. So I need to write r in terms of H. So in the blue, we've got little r is capital R over capital H times H. Now we add up all such slices. That's going to give us a Riemann sum. Then the number of slices will go to infinity in our Riemann sum, and that becomes our definite integral, which we're going to label the total. In the Riemann sum, we have a discrete delta H, but in the definite integral, our discrete delta H becomes the continuous dH. And we just have to integrate over all the values of H that are in play. So we have to do this calculation, area times height, for all the values of H that we have area. The lowest value is 0, the highest value is H. So we'll integrate from 0 to capital H. Now we might simplify this definite integral by factoring out everything that's a constant. So I've got pi r squared over an h squared. And then we'll integrate from 0 to h. Oops, sorry, capital H. The h squared, little h squared. Now we can see where the 1/3 is going to come from. Now we can see where these h's are going to go. We can see that the integration is going to give us an h cubed. And we can see that this h squared is going to take out 2 of them. And we can also see where the 1/3 is coming from. So then we can actually calculate this. So we get pi r squared over h squared times 1/3 h cubed from 0 to capital H. So it's going to be pi r squared over h squared, capital H squared, times 1/3 capital H cubed minus 1/3 of 0. We should note that we collectively, like the collective, we have known the volume of a cone longer than we've known about calculus. Volume of a cone was answered way before calculus came along. But it's nice that the new tool that comes along, calculus, still fits and works on our old knowledge. Let's just quickly break down a student standpoint of what you want to look for. And this is a lot to write down. And you're like, oh, Leach, am I going to have to write all this down? And the answer is no. Here is how I will score one of these problems when you write one of these problems for you. Here's the first thing I look at. The first thing I look at is what you say is the volume or whatever I'm asking you to look for. I'll usually say round this answer to 5 significant figures. If your answer is accurate to 5 significant figures, you probably did not fuck it up so badly. It's unlikely that you just randomly guessed 5 significant figures and actually got the right answer. If you did, you know what? You win. That's it. You just win that round. If you just critical hits, whatever. So the next thing I look for is your integral. I look for a definite integral that led you to this answer. The main thing that I'm looking for here is the interval over which you are integrating. I don't know why, but I consider it to be kind of an important part of the problem. It's understanding the integration process by coming up with the correct interval over which you are integrating. Then I look at what you claim is the volume of the slice. Are you using the right base model, pi r squared? Do I see a pi r squared in your development? Then I will look at your diagram and see if you have defined your variables and if you're labeling your variables correctly. The number one place that students go wrong when they attempt these problems is they have a diagram, they have some function of little h, and the diagram has no h involved. And the first thing I always ask, oh, what's h? And you're like, oh, it's the variable. It's like, oh, what's the variable represent? And you're like, oh, it's the height. Show me, just label it. You don't label what the h is. And that's where things go wrong. So those are the things that I look for in that order. Answer, definite integral, focusing on the interval, your development, your diagram. Diagram, development, definite integral. This should be a D, but it's just answer. No, shit. The answer. The 4 Ds of applications of integration. Tomorrow, we're going to do more of this. I'm going to move this H because we have freedom to decide where H goes. So good news, we have freedom to decide where H goes. Bad news, we have freedom to decide where H goes. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.